real differentiation. So the Laplace of the nth derivative of f of t is given by the formula s raised to n multiplied by f of s minus s raised to n plus 1 multiplied by f at 0 time minus s raised to n minus 2 multiplied by the derivative of f at 0 time minus and so on up to the n minus 1 derivative of f at 0 time. For real integration, the Laplace of the nth integral of f of t is equivalent to f of s divided by s raised to n plus the first integral of f at time t equal to 0 minus over s raised to n plus the second integral of f at 0 minus over s raised to n minus 1 plus and so on up to the nth integral of f at 0 time over s. It's also important to take note of the initial value theorem defined as the limit of f of t as time t reaches 0 equal to the limit of s multiplied by f of s as s approaches infinity. And correspondingly, the final value theorem defined as the limit of f of t as time t reaches infinity equal to the limit of f of s times s as s approaches 0. To solve the differential equation using Laplace transform, we obtain its Laplace transform, apply the initial conditions, and solve for y of s algebraically, thus giving us y of s equal to a numerator in terms of s and a denominator in terms of s. Here we need to apply partial fraction expansion on y of s before getting the inverse Laplace transform from the given table. In applying partial fraction expansion, we need to examine the resulting factors in our denominator. If the factors gives us roots that are real and distinct, that will give us case number 1, which means the expansion is generally given by a over quantity s minus p sub 1 plus b over quantity s minus p sub 2 plus and so on depending on the number of factors that are real and distinct roots. We can solve for the coefficients a, b, and c, and so on, using the formula a equal to the value for y of s multiplied by the denominator of a as s minus p sub 1 and letting s equal to p sub 1. And similarly, we can solve for the coefficient b by multiplying y of s by the denominator of b equal to s minus p sub 2 and letting s equal to p sub 2. Once the coefficients are obtained, it's easy to obtain now the corresponding inverse Laplace transform, which will give us y of t equal to a e raised to p sub 1 times t plus b e raised to p sub 2 times t plus and so on, again depending on the number of terms in the factors of our denominator. If the factors of our denominator results to roots that are real and equal, it falls under case number 2. So that gives us the general form for the expansion given by the expression a sub 1 over quantity s minus p raised to n plus a sub 2 over quantity s minus p raised to n minus 1 and so on up to a sub n over quantity s minus p. And we can solve the coefficients in general as a sub n equal to 1 over quantity n minus 1 factorial multiplied by the n minus 1 derivative of the product of y of s multiplied by quantity s minus p raised to m. Take note that m is the highest value of n. And to solve for the coefficients a sub n, we let s equal to the root p. In general, the resulting output y of t is given by the inverse Laplace transform a sub 1 over quantity n minus 1 factorial multiplied by e raised to p times t raised to n minus 1 plus a sub 2 over n minus 1 quantity factorial multiplied by e raised to p times t then times t raised to n minus 2 plus and so on up to a sub n e raised to pt. Case 3 results if the resulting factors of our denominator produces complex and conjugate roots. And that leads us to the general expansion given by a sub k over quantity s minus sigma minus j omega d plus a sub k plus 1 over s minus sigma minus j omega d. The coefficients a sub k and a sub k plus 1 can be easily solved using the same rule as for case 1. But in this case, the expected coefficients are complex and conjugate coefficients. So once the coefficients are now obtained, we have the general expected y of t or inverse Laplace transform given by a sub k e raised to quantity sigma plus j omega d closed quantity times t plus a sub k plus 1 e raised to quantity sigma minus j omega d closed quantity multiplied by t. The resulting y of t for case 3 can actually again be combined into a single term using the formula which we have derived earlier. So meaning y of t is equal to a total e raised to sigma t sine of quantity omega dt plus the angle alpha. And as defined, a total is actually the square root of the sum of the coefficients a sub k and a sub k plus 1 squared plus the square of the product of j multiplied by quantity a sub k minus a sub k plus 1. And the angle alpha is actually the angle theta, the inverse tangent of the sum of the coefficients and the difference of the coefficients multiplied by j. Plus, we add angle 0, 180 or 360 depending on which particular quadrant the angle theta falls. As an example, consider the problem we had under our classical method solution. Second derivative x of t plus 3 times first derivative x of t plus 2x of t equal to 1 plus t. And here the initial conditions are assumed to be x at 0 time is equal to 0 and the first derivative of x at time t equal to 0 is equal to 1. So by taking the Laplace of the second derivative of x of t using the formula gives us s squared times x of s minus s as x at 0 time minus the first derivative of x at t equal to 0 time. And similarly, the Laplace of the first derivative of x at t is equal to s times x of s minus x at 0 time. And Laplace of x of t is equal to x of s. And on the right side, using again the table of Laplace transform, the Laplace of 1 unit step is 1 over s, and the Laplace of the 1 unit ramp is equal to 1 over s squared. By substituting and applying the values we have obtained using Laplace transform and applying the initial conditions, that leads us to the expression s squared x of s minus 1 plus 3s x of s plus 2x of s on the left side equal to 1 over s plus 1 over s squared on the right side. Obtaining the common denominator on the right side leads us to s plus 1 over s squared. Solving for x of s, we can simplify the expression as s squared plus 1 plus s divided by s squared multiplied by quantity s squared plus 3s plus 2. From the resulting x of s, we apply partial fraction expansion, and given the denominator, we know that the factors are s squared, s plus 1, and s plus 2. S squared gives us case 2, whereas s squared plus 3s plus 2 gives us factors s plus 1 and s plus 2 with roots equivalent to negative 1 and negative 2. And this falls under case number 1. So the expansion is given by a over quantity s plus 1 plus b over quantity s plus 2. And for case 2, we have the coefficient c1 over s squared and c2 over s. So solving for a, using the formula which we have discussed earlier, we multiply x of s by the denominator of a, and we let s equal to negative 1. So the resulting value of a gives us 1, and similarly for b, we multiply x of s by s plus 2, and we let s equal to negative 2. So from which we can obtain b by applying the value for s equal to negative 2, it gives us negative 3/4. For the last two coefficients, c sub 1 and c sub 2, for c sub 1, we simply multiply x of s by the coefficient of c1 and we let s equal to 0. And that gives us c sub 1 equal to 1/2. Then for c sub 2, since n is equal to 2, we obtain the n minus 1 derivative of the product of x of s times s squared and multiply it by 1 over n minus 1 quantity factorial. And to solve for c2, we let s equal to 0. And this leads us to the value for c2 equal to negative 1/4. By replacing these coefficients by the resulting values, we come up with x of s equal to 1 over quantity s plus 1 minus 3/4 over quantity s plus 2 plus 1/2 over s squared minus 1/4 divided by s. Applying inverse Laplace transform for each of the given terms will give us the time domain value for x total. And that gives us e raised to negative t minus 3/4 e raised to negative 2t plus 1/2 times t, then minus 1/4. Several examples are also given, the same as what we have in our classical method solution for comparison.